Welcome! In this video, we will explore LeetCode problem number 2139, titled Minimum Moves to Reach Target Score. This problem challenges us to determine the minimum number of moves required to reach a given target score starting from 1. We'll break the problem down step by step, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, you are playing a number game where you start with the number 1 and aim to reach a given target number. To do this, you have two types of moves available. First, there's the increment move, which allows you to add 1 to your current number. Second, there's the double move, which lets you multiply your current number by 2. However, the double move comes with a limitation: you can only use it a certain number of times, determined by the value of max doubles. Once you've used up all your allowed double moves, you can only rely on increment moves to reach the target. Your goal is to figure out the minimum number of moves required to get from 1 to the target number, given these constraints. To solve the problem, you'll take two inputs: the target number, which is the value you're trying to reach, and max doubles, which specifies the maximum number of times you can use the double move. The output is a single integer, representing the minimum number of moves needed to reach the target. Let's look at some examples to better understand how this works. In the first example, the target is 10, and you're allowed up to 4 double moves. Starting at 1, the first move is to perform a double move, which multiplies 1 by 2, resulting in 2. Next, you perform another double move, multiplying 2 by 2, which gives you 4. Then, you use yet another double move, taking 4 to 8. At this point, you're close to the target but need to add 2 to reach 10. This is done with 2 increment moves, each adding 1, to get from 8 to 10. Altogether, you've used 3 double moves and 1 increment move, for a total of 4 moves. This is the minimum number of moves required to reach the target in this case. Now let's examine a scenario where the number of allowed double moves is more restrictive. In the second example, the target is 19, but you're limited to only 2 double moves. Starting from 1, you perform a double move to reach 2, and another double move to reach 4. At this point, you've used all your allowed double moves. To reach the target of 19, you must rely entirely on increment moves. From 4, you add 1 repeatedly, 15 times in total, to reach 19. This results in a total of 2 double moves and 15 increment moves, making 7 moves overall. Notice how the limited number of double moves significantly impacts the strategy and the number of moves required. The third example illustrates what happens when no double moves are allowed. Here, the target is 5, and max doubles is 0. Since you cannot use the double move at all, the only way to reach the target is through increment moves. Starting from 1, you add 1 4 times to reach 5. This results in a total of 4 increment moves. This example highlights how the absence of double moves forces you to rely entirely on increment moves, making the solution straightforward but potentially less efficient for larger targets. In this problem, there are several important constraints and edge cases to consider. For instance, if max doubles is 0, the only way to reach the target is by using increment moves, which makes the number of moves equal to target minus 1. On the other hand, if the target is very large and max doubles is small, you need to maximize the use of double moves to minimize the remaining distance, which must then be covered by increment moves. Another interesting case is when the target is a power of 2. In these situations, you can potentially reach the target using only double moves, provided that max doubles is sufficient. Lastly, if you use up all your allowed double moves before reaching the target, you'll need to rely on increment moves to cover the remaining distance. These considerations are key to finding the optimal solution for any input scenario. To solve the problem of reaching a given target number starting from 1, we need to minimize the number of moves by strategically using the 2 allowed operations, incrementing and doubling. Incrementing simply adds 1 to our current value, while doubling multiplies the current value by 2. However, doubling is restricted because it can only be used a limited number of times, defined by max doubles. The key challenge here is to minimize the overall number of moves while making the best use of the limited doubling operations to close the gap to the target as efficiently as possible. Understanding this balance is critical to solving the problem optimally. One approach to solving this problem is the brute force method. Here, we simulate all possible sequences of moves starting from 1 and evaluate every combination of increments and doubles to reach the target. At each step, the algorithm decides whether to increment or double based on the remaining doubling capacity. While this method guarantees finding the minimum number of moves by exploring all possible paths, it comes with a significant drawback: its exponential time complexity. With the number of decision points growing rapidly as the target increases, this approach becomes computationally infeasible for larger targets, such as those near 10 to the power of 9. While conceptually straightforward, brute force is simply not practical for this problem. A more efficient approach is the greedy strategy, which works backward from the target to 1. Instead of building up from 1, we reduce the target step by step. If the target is even and we still have doubling operations left, we reverse the doubling process by dividing the target by 2. This is the most effective way to close the gap quickly. If the target is odd, we perform the reverse of an increment by subtracting 1 from the target to make it even. This process continues until we reduce the target to 1, keeping track of the total moves and the number of remaining doubling operations. By working backward, we eliminate unnecessary computations and focus on the most impactful operations first. The time complexity here is logarithmic, as we are having the target whenever possible, making this approach highly efficient for large inputs. Another potential approach involves dynamic programming. In this method, we define states based on the current number and the remaining doubling operations, and calculate the minimum moves required for each state. The transitions between states depend on whether we choose to increment or double. This ensures that overlapping subproblems are solved only once, making the solution systematic and guaranteeing optimality. However, the dynamic programming approach comes with its own trade-offs. Its time and space complexity are proportional to the target and the maximum number of doubling operations, which makes it significantly less efficient than the greedy approach for this specific problem. While it is a feasible solution, it introduces unnecessary overhead for a problem that can be solved more elegantly with a greedy algorithm. The chosen solution for this problem is the greedy approach, which involves working backward from the target to 1. This method is both simple and efficient, as it prioritizes reverse doubling to close the gap quickly whenever possible. By focusing on having large numbers, we minimize the total number of moves. Incrementing is used only as a fallback when halving is not an option, such as when the number is odd or when doubling operations are exhausted. Key insights that make this approach effective include recognizing that doubling has the greatest impact when the numbers are large, and that working backward avoids unnecessary computations. Compared to brute force and dynamic programming, the greedy method stands out for its balance of simplicity, efficiency, and correctness. With a logarithmic time complexity, it is perfectly suited for handling the problem's constraints, including very large targets. To tackle the problem minimum moves to reach target score, we need to minimize the number of operations required to transform the number 1 into a given target value. We have 2 operations at our disposal: the increment move, which adds 1 to the current number, and the double move, which doubles the current number. However, there's a catch: double moves are limited by the max doubles parameter, meaning we can only use this operation a fixed number of times. A key insight here is to approach the problem in reverse. Instead of figuring out how many operations it takes to build up to the target from 1, we simplify the task by calculating how many moves are necessary to reduce the target back to 1. This backward approach allows us to focus on eliminating larger chunks of the target efficiently, especially through division, whenever possible. The algorithm starts by initializing a moves counter to 0. This will keep track of the total operations we perform. Now, as long as the target is greater than 1, we repeatedly reduce it using the 2 operations. If we still have double moves available and the target is even, we divide the target by 2, which is essentially the reverse of a double move. If the target is odd, we subtract 1 to make it even, preparing it for division in the next step. Each of these operations increments the moves counter. Every time we perform a double move, we also decrement the max doubles count. Once we run out of double moves, or if the target becomes 1, we resolve any remaining difference between the target and 1 using increment moves. Since each increment move corresponds to a subtraction of 1, we simply add the difference, target 1, to the moves counter. Finally, the algorithm returns the total moves as the result. This approach ensures we minimize operations by prioritizing division, which halves the target, over subtraction. This greedy backward approach works effectively because it leverages the properties of division. Dividing by 2 is only possible when the number is even, which naturally forces us to handle odd numbers through subtraction first. This aligns perfectly with the constraints on double moves, ensuring that we use them optimally. Once max doubles is exhausted, the algorithm seamlessly shifts to using only increment moves. A few key edge cases to consider include scenarios where max doubles is 0, in which case the algorithm defaults to subtracting 1 repeatedly. If the target is already 1, no operations are needed. On the other hand, if the target is very large but we have sufficient double moves, the algorithm minimizes increment moves by relying heavily on division. In terms of implementation, we only use a few integer variables to track the target, max doubles, and moves, making the algorithm simple and memory efficient. The time complexity is logarithmic, as each division by 2 halves the target, and the space complexity is constant, utilizing no additional data structures. Let's walk through some examples to solidify our understanding. For the first example, with target equals 10 and max doubles equals 4, we start with 0 moves. The target is even, so we divide it by 2 to get 5, incrementing the move counter to 1 and reducing max doubles to 3. Since 5 is odd, we subtract 1 to make it even, setting the target to 4 and increasing moves to 2. Next, we divide 4 by 2 twice, reducing the target to 2 and then to 1 while incrementing moves to 4. The result is 4 moves. In the second example, with target equals 19 and max doubles equals 2, we again start with 0 moves. Since 19 is odd, we subtract 1 to get 18 and increment moves to 1. Then, we divide 18 by 2 to get 9, reducing max doubles to 1 and moves to 2. The target is odd, so we subtract 1 to get 8, then divide by 2 twice more, exhausting max doubles and reaching 4. Finally, we subtract 1 3 times to reach 1, bringing the total moves to 7. These examples highlight how the algorithm balances division and subtraction to minimize operations while respecting the constraints. This code solves LeetCode problem number 2139, minimum moves to reach target score, by working backward from the target to 1. The goal is to minimize the number of operations, either subtracting 1 or dividing by 2 when the number is even, and the number of allowed double moves is not exhausted. Step-by-step explanation. 1. Initialization. We start with a variable move set to 0 to track the total number of operations performed. 2. Backward traversal. The algorithm works backward from target to 1. This is efficient because we can directly address the key operations, divide by 2 or subtract 1. 3. Handling even numbers. If the current target is even and we still have max doubles available, we perform a division by 2. This reduces the number faster while consuming 1 double move. 4. Handling odd numbers. If the current target is odd, we subtract 1 to make it even. This is necessary because division by 2 is only applicable to even numbers. 5. No more double moves. If max doubles reaches 0, we can only use subtraction. In this case, the remaining distance to 1 is reduced directly by adding target 1 to moves, as all intermediate steps will involve subtracting 1. 6. Increment moves. After every operation, either subtracting 1 or dividing by 2, we increment the moves counter. 7. Return result. Once target reaches 1, the loop exits, and the total number of moves is returned. Key insights. The algorithm prioritizes division by 2 when possible, as it is the most efficient way to reduce the target. By working backward, we avoid unnecessary calculations and directly focus on the required operations. This approach ensures that the solution is optimal and efficient, with a time complexity of approximately O log target due to repeated divisions by 2. This is the Java implementation of the minimum moves to reach target score problem on LeetCode. The logic mirrors the Python solution, working backward from the target to 1 while minimizing moves. The key differences include explicit type declarations and the use of Java's class structure. This implementation maintains the same logic flow, ensuring correctness and clarity. Here, we begin with the first example where the target is 10, and we can double up to 2 times. Initially, we have target equals 10, max doubles equals 2, and moves equals 0. Since the target is even and we still have doubling operations available, we divide the target by 2. This gives us target equals 5, reduces max doubles to 1, and increments moves to 1. Now, target equals 5 is odd, so we subtract 1 to make it even. This updates the target to 4 and increments moves to 2. At this point, the target is even and we still have one doubling operation left. Dividing the target by 2 results in target equals 2, reduces max doubles to 0, and increments moves to 3. At this stage, the target is 2, which is even, but we can no longer use the doubling operation since max doubles equals 0. Instead, we subtract 1, reducing the target to 1 and incrementing moves to 4. Once the target becomes 1, we stop, and the final output for this example is moves equals 4. Now, let's move to the second example, where the target is 19 and we can double up to 2 times. Initially, target equals 19, max doubles equals 2, and moves equals 0. Since the target is odd, we subtract 1 to make it even. This gives us target equals 18 and increments moves to 1. With the updated target of 18, which is even and still allows doubling, we divide it by 2. This results in target equals 9, reduces max doubles to 1, and increments moves to 2. The target is now 9, which is odd, so we subtract 1 to make it even again. This updates the target to 8 and increases moves to 3. Now, with target equals 8, which is even and still allows one more doubling operation, we divide by 2. This results in target equals 4, reduces max doubles to 0, and increments moves to 4. At this point, the target is 4, an even number, but we can no longer double. So we subtract 1 repeatedly to reduce the target to 1. Subtracting 1 3 times updates the target to 3, then to 2, and finally to 1, while moves increase to 5, 6, and 7, respectively. When the target finally reaches 1, we stop the loop, and the total number of moves for this example is moves equals 7. For the third example, the target is 5, and we cannot use any doubling operations since max doubles equals 0. Starting with target equals 5 and moves equals 0, we simply subtract 1 repeatedly until the target becomes 1. Subtracting 1 4 times reduces the target from 5 to 4, then to 3, to 2, and finally to 1, while moves increment from 0 to 4. Once the target reaches 1, we stop, and the final output for this example is moves equals 4. To analyze the time complexity of this solution, we need to examine the main operations performed by the algorithm. The algorithm works by iteratively reducing the target number, using either division by 2 when the target is even and we still have available max doubles, or subtraction by 1 when the target is odd or when no more divisions can be performed. Each iteration involves one of these operations. Now, the number of iterations depends on the balance between these two operations. If max doubles is greater than 0, the number of divisions is limited to at most max doubles since each division consumes one doubling operation. Once all doubling operations are exhausted, the algorithm transitions to performing only subtractions. In the worst-case scenario, where the target is reduced entirely through subtractions, there could be up to target 1 iterations. Combining both cases, the total number of iterations is influenced by the logarithmic reduction from divisions and the linear reduction from subtractions. When target is large and max doubles is small, subtractions dominate, leading to an upper bound on the time complexity of O, target. Mathematically, we can further justify this analysis. In the best case, when max doubles is sufficiently large, the algorithm can repeatedly divide the target by 2 until it reduces to 1. Since dividing a number by 2 repeatedly takes logarithmic steps, the total number of iterations is proportional to log, target. On the other hand, in the worst case, when max doubles is 0, the algorithm must rely solely on subtractions, resulting in up to target 1 iterations, which gives a time complexity of O, target. Combining both cases, the overall time complexity is the sum of O, log, target, for divisions and O, target, for subtractions. However, since O, target, dominates as target becomes large, the final time complexity simplifies to O, target, in the worst case. As for space complexity, the algorithm uses only a constant number of variables, namely moves, target, and max doubles. It does not rely on recursion or any additional data structures, resulting in a space complexity of O(1). This makes the algorithm highly space efficient, regardless of the input size.
Comparing this optimized solution to a brute force approach highlights its efficiency even further.
A naive approach would simulate every possible sequence of moves from one to the target, exploring all combinations of doubling and incrementing. This method results in exponential growth in the number of states to evaluate, leading to a time complexity of 2 target. In contrast, our solution takes a more strategic approach by working backward from the target and prioritizing division over subtraction whenever possible. This drastically reduces the problem size and improves the time complexity to target. By leveraging division, which is more efficient than subtraction, the algorithm minimizes the number of iterations required to reach 1. When analyzing best, average, and worst cases, the best case occurs when max doubles is large enough to repeatedly divide the target by 2, leading to a logarithmic time complexity of log target. In the average case, a mix of divisions and subtractions yields a time complexity of target. Finally, in the worst case, where no doubling is possible, the algorithm relies solely on subtractions, resulting in target time complexity. This thoughtful optimization ensures the solution is far more efficient than brute force methods. In conclusion, the provided solution is both time and space efficient. It achieves a linear time complexity of target in the worst case, while the best case can achieve logarithmic complexity depending on the availability of max doubles. With constant space complexity of 1, the solution avoids the overhead of recursion and additional memory usage, making it highly scalable for large inputs. This represents a significant improvement over the brute force approach and demonstrates how focusing on the most efficient operations can drastically improve algorithmic performance. Overall, the solution is well suited to handle the constraints of this problem efficiently and effectively. When solving this problem, there are a few common mistakes that can trip you up. First, not prioritizing division moves. A lot of beginners get fixated on additive moves, incrementing by 1 to reach the target, but this approach is inefficient. Division by 2 reduces the target exponentially, which is much faster than the linear progress made by addition. The key is to always prioritize division when the target is even, and only use additive moves when the target is odd or division is impossible. Another frequent error is mishandling the base cases. For instance, if you don't handle cases like when the target becomes less than 1 or when it's reduced to exactly 1, your solution might enter an infinite loop or produce incorrect results. To fix this, it's important to carefully define and handle these edge scenarios so your solution terminates correctly and gives the right answer. Another mistake to watch out for is relying too heavily on a greedy approach without fully considering edge cases. For example, with very large target values or when division is repeatedly blocked by odd numbers, a naive greedy solution can overlook scenarios where incrementing first and then dividing results in fewer moves overall. It's important to test your solution on edge cases, like a target of 10,000 or 15, to ensure it handles these situations correctly. Additionally, avoid inefficient iterative implementations. Iterating from 1 to the target can lead to unnecessary computations and higher time complexity. Instead, work backwards from the target to 1, which aligns better with the constraints of this problem. Finally, don't ignore the impact of the max doubles constraint. If you try to divide without checking whether max doubles is greater than 0, your solution may fail to terminate or might require more moves than allowed. Always ensure that division moves are used strategically within the limit of max doubles. To solve this problem effectively, the key insight is to use a greedy backward approach. By starting at the target and working backwards to 1, you align your operations with the problem's constraints naturally. This strategy prioritizes exponential reductions through division over linear increments, which is the most efficient way to reduce the target. Interestingly, this problem combines principles of both greedy algorithms and dynamic programming. While the greedy approach is more intuitive and efficient, you can also discuss the trade-offs with a forward dynamic programming approach, which ensures correctness but is less optimal in terms of time complexity. When explaining your solution, be prepared to address edge cases. For example, how does your solution handle very small targets like 1, very large targets like 10,000, or scenarios where max doubles is 0? Additionally, this problem is closely related to others on LeetCode, such as problem 991, the broken calculator, which also requires a greedy backward strategy, and problem 1347, which shares the theme of minimizing operations, albeit in the context of strings. There are also connections to other problems that involve similar decision-making.
For example, problem 650, the two-keys keyboard, requires careful choices between different operations to reach a target, and problem 1217 focuses on minimizing moves under specific constraints. When it comes to alternative approaches, you could consider using dynamic programming in a forward direction.
In this approach, you define a DP array where each entry represents the minimum moves needed to reach that value from 1. While this ensures correctness, the trade-off is that it's less efficient, with target, time and space complexity. A better alternative is the iterative greedy approach, where you work backwards from the target, prioritizing division by 2 when max doubles is available. This method is optimal, with logarithmic time complexity and constant space.
Lastly, you could explore a recursive greedy approach with memoization. This involves exploring all paths recursively while storing results to avoid redundant calculations. However, it's harder to implement and generally less efficient than the iterative greedy method. For this problem, the iterative greedy approach strikes the best balance between simplicity and performance. Thank you for following along.
In this video, we covered LeetCode problem number 2139, minimum moves to reach target score.
We summarized the problem, outlined an optimal solution, and discussed key concepts. Don't forget to practice similar problems to reinforce what you've learned.
If you enjoyed this, please like and subscribe for more problem-solving content.
See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!